introduction. Sorry, there we go, yeah, I think I jiggled the wires, but we're back, good. Good morning, everyone. Before I begin, I'd like to acknowledge my co-author, Mike van der Panne, who did his master thesis with me, and this is his experimental work I'm going to be discussing. And as you see, I also have a question mark in the title, but don't worry, I do have an answer for you, but also some more questions. And so, what is related to? Well, fatigue delamination growth. Over the past 2 to 3 decades, when we've been studying that, we've been relying on these standardized test geometries, DCB, ENF, and so on. But why? I mean, if we look around this room, I don't see any DCB specimens, right, in the structure of the building. Of course, the answer is that we hope to learn something from these standardized tests that we can generalize, that we can transfer to full-scale composite structures. However, as I pointed out also last time at VCF, there are quite some differences between the standardized tests and full-scale structures, and if we don't take those into account, we really need to ask, what can we actually learn? And today I want to focus on one point, which is that the standardized tests all use unidirectional laminates, where the delamination is in a plane between two fibers with the same, or between two plies with the same fiber orientation. Whereas in a full-scale structure, typically we have a multi-directional laminate, and we get delaminations precisely in planes or in interfaces between different fiber orientations. So if we want to take what we learn from our standardized testing and apply it to full-scale structures, then we need to ask, is this unidirectional testing enough? Or do we somehow need to take this fiber orientation effect into account? Well, there's some background that we could already rely on from the literature, because the quasi-static case has already seen quite some study. There's a nice summary of that in the introduction to the paper by Blondeau and co-workers that I quote there. And the short version of that introduction is that the initiation fracture toughness, and so this is the quasi-static initiation, that is independent of the fiber orientation, whereas the propagation fracture toughness, the R-curve behavior, does depend on the layup. And the reason given for that is that initiation happens in a small resin-rich area, far away from any fibers, at the microscale, far away that is, whereas the R-curve behavior is driven by fiber bridging and crack migration effects, and those then depend on the layup. And some examples from the literature. If we look at the top here, we have a crack progressively migrating away from the midplane, whereas at the bottom here we have an oscillatory behavior where we have a crack migrating between two 0-90 interfaces and kind of shifting up and down between those. So that is quasi-static. In fatigue, there's much less data. In terms of multi-directional delamination, I could find some work from the group of Professor Bang-Sils, who we just heard. There's also some work from China by Zhao et al. And Kong et al. But there are no direct comparisons between a unidirectional interface and a multi-directional interface for the same material. So we can't really extract what is the effect of the fiber orientation. So we decided that's a nice knowledge gap to jump into. Let's see if we can do some first tests, get some first preliminary data to have an idea what is going on here. Before I discuss that with you, however, I want to take a brief detour into the question of fiber bridging in fatigue. Also came up again this morning during the plenary. Because from the quasi-static case, we could expect that fiber bridging also in fatigue would play an important role. And what we see, if we just do a unidirectional test, this is data from Liao Junyao, where we have our crack growth rate vertically, our strain energy release rate range horizontally, so this is the Paris curves. And if you now do multiple tests on the same specimen, so with progressively longer crack lengths, or pre-crack lengths, you see that these curves shift to the right. And that is because as the crack length gets longer, you're developing more fiber bridging, and this fiber bridging has a shielding effect that slows down the crack growth rate. And that works until eventually you get to a certain crack length where even longer crack lengths no longer result in a reduction of the crack growth rate, so you get a kind of saturation of the fiber bridging behavior. And as was already discussed, there's been quite some discussion over the past years what to do with this fiber bridging, because it's usually claimed that this is an artifact of the test procedure. The argument I've usually heard is in full-scale structures, we have multi-directional laminates, therefore no nesting of the fibers, therefore no fiber bridging. And therefore we should find some way to get rid of this. To be honest, I haven't seen much evidence either way of full-scale structures. I understand the reasoning, but I haven't seen actual fractographic evidence. And I think, based on what I'm about to show you, we should maybe reopen that question and really look what actually happens in full-scale structures. So, what did we then do? Well, we did standardized DCB tests, the same way everybody else does them in the literature, but with different layups to give us different interfaces at the midplane where the delamination will occur. And today I only have time to show you one series. That is the series with a 0,0 interface, a 0,45 interface, and a 0,90 interface. But we also tested some other series, so with parallel fibers but at different angles to the axial direction, and with a 90-degree jump between the fibers and then different orientations. And I can show you that data later if you want. But for the data I'm going to show you, we had 2 specimens per interface, and then 2 tests per specimen. Why 2 tests per specimen? Like the plenary this morning, we did 1 test with a short pre-crack length, so starting from the Teflon insert, quasi-static loading to open the crack, and then immediately a fatigue test. Then another quasi-static loading to grow to a long crack length, and then again another fatigue test on the same specimen. And what you get is then the following. This is for the 0,0 case. What we see is on the left here, the 2 short pre-crack tests, on the right the long pre-crack tests. And as we would expect, there's also a difference here for the short pre-crack tests in the crack length, and the curve shifts to the right for the longer pre-crack length. Whereas if we have a really long pre-crack, then we see the pre-crack length no longer affects the results, the curves are on top of each other, so we have a saturated fiber bridging behavior, is at least our interpretation. And if we look at what the specimens look like, on this beamer is a bit hard to see, but this is the classical fiber bridging with lots of individual fibers spanning the gap between the 2 crack flanks, thereby bridging the crack and slowing down our crack growth. Now, for the interesting part, the 0,45 test. What we see for the short pre-crack lengths is that we are more or less on top of the previous tests, but for the long pre-crack length, and actually quite a bit shorter than the long pre-crack length in the 0,0 case, we are much further to the right. So the fiber bridging effect, or we can discuss whether it's fiber bridging or something else, we'll get to that in a second, but the crack growth effect, or slowing effect, is much stronger for the 0,45 case than for the 0,90 case. And if we look at our specimens, then what we see is actually something quite different in terms of the fiber bridging behavior. So we have all these individual fibers, but we also see these bundles being pulled out. And we can argue, is this fiber bridging or is it a crack migration? What should we call it? But in any case, it's different to what we saw for the 0,0 case, and it appears to give us a stronger slowing of the crack growth rate. Then finally, the 0,90 case. Here, for the short pre-crack lengths, we are on the right-hand side compared to the previous data, but we also have a relatively long pre-crack in this case, so it's not entirely clear, is this an orientation effect or a pre-crack length effect? But here for the long pre-cracks, again, we appear to be saturated because we have, 12 millimeter difference, but on top of each other more or less, and we're in between the 0,0 and the 0,45. So we have a stronger slowing of the crack growth than for the 0,0 case, but slower than for the 0,45. Why is that? Well, we can form a hypothesis if we look at what's going on, because here the fiber bridging had much more the character of an oscillatory migration between the 2 0,90 interfaces on either side of the 90-degree ply. That gives you a crosswise pullout of short bundles, which you can kind of see over here. But of course, the length of those bundles is limited by the edge of the specimen. So in a 0,45 interface, we can form much longer bundles than in a 0,90 specimen. And I suspect that is the reason that we see a difference in the crack growth slowing. So that was all rather fast, so let me summarize the key points. We saw fiber bridging and or delamination migration for all the interfaces we tested, including the ones I didn't show you today. So that suggests to me we should really rethink our assumption that it doesn't occur in full-scale structures. The fiber orientation affects both the nature and the strength of this fiber bridging and migration behavior. And by strength, I mean how much does it slow the crack growth rate. And we could say, well, we rely on 0,0 data because it was conservative, right? It was always to the left. But it's likely over-conservative. So if we can rely on this fiber bridging, and I know in the wind turbine sector people are moving towards that, but if we can rely on fiber bridging and can predict it, then potentially we could allow for higher stresses in our structures. And finally, to answer the question, in my view, unidirectional testing is insufficient to understand what is going on in fatigue delamination in full-scale structures. So, as I said, I have an answer for you, but also many questions to open. If you'd like to join in investigating that and have a head start, you can go to this link, and in a couple of weeks, hopefully, you'll find the data there. I need to clean up the documentation, but then it will be online and available for everyone. If you can't find it yet, drop me an email. I'm happy to give you access in a different way. And I hope that you will join me in investigating this fiber orientation effect, so that we as a community can really start to understand how do we go from our standardized specimens to full-scale structures. Thank you very much.